In this lecture, we will be going over the concept of cross-validation. For this lecture, you are expected to have read Chapter 5 of An Introduction to Statistical Learning with Applications in R. The Chapter 5 is on resampling methods, which includes cross-validation. So if you have not read that, stop, go read it, and then come back to this lecture. Today we'll go over three primary topics: the goals of cross-validation, leave one out cross-validation, and k-fold cross-validation. We start with the concept of cross-validation itself. It helps to understand cross-validation by thinking back to the goals of estimating a particular model. We've gone over the idea of using models to infer the structure of relationships between X and Y, or to predict Y using X. Now, those have been discussed as separable goals. You can actually intertwine them by trying to understand models that best predict Y. So you can use prediction as a way of inferring inference or answering inference questions. Let's think back to the idea of using statistical models to infer relationships between X and Y. In inference questions, you typically ask, what is the probability that the null hypothesis is true? So you have a model, you have the null variant of that model, and typically we estimate p-values that tell us whether or not a particular set of data can reject the null hypothesis. So you estimate a likelihood distribution of the null, or more appropriately, you estimate the likelihood of the data that you see given that the null hypothesis is true. You have some p threshold, which is determined by your alpha. So for example, you might have an alpha of 0.05, so you want to set your p-value 0.05, which says that once you cross the probability of 5% that you would see the data that you have given that the null hypothesis is true, then you can reject the null hypothesis and say that you infer that your current model is correct, the non-null model is correct. This is the way we typically use inference models with null hypothesis test statistics. There's another way of asking an inference question. In that case is, what is the probability that a prediction from my model, y hat, predicts what I observe, y, better than chance? Or in this case, chance just being the mean of y. How does this really get us at an inference question? Well, what you would do is you would learn some model of some particular form on a set of training data, and you've learned to kind of build those predictions. And you would test how well that training model, or that model that was learned in the training data set, predicts y in your test set evaluation. There's actually a null in this evaluation. We typically ask whether or not the residual sums of squares is substantially smaller than the total sums of squares. Another ways of putting it is that the null hypothesis for a model in the prediction context is that your model fits, your y hats, won't do any better at predicting y than the mean of y. This is a way of framing a null hypothesis in the context of prediction. Now, the way that you would build an inference here is by comparing multiple variants of your model, your regression coefficient with different variables of x, and ask which one best explains or best predicts y. We will go over how to do this in future lectures, but the key concept here is that you need to have some ability to do an holdout test evaluation of your model predictions in a completely independent data set than what was used to fit your model. We went over this a lot when talking about the bias-variance trade-off. So the idea that you want to find that nook in your test set error curve that best manages the bias variance trade-off. And in order to do this, you need to have internal validation sets. You need to have subsets of the data that you can kind of divide it into to have training sets and test sets. And this is an alternative to the way that you might traditionally think about this, where you collect two different versions of your data set altogether. If you're doing an experimental study, running a study, learning the model, and then running a replication study and seeing how well you can predict in that replication set. That's all nice and good, but oftentimes you only have one data set. So how can you ask these types of validation set questions with the data set that you have? Remember, our goal is to estimate out the residual sums of squares. So our goal is to try to minimize this residual sums of squares of your predictions. And so in the classic test error case, what you're doing is you're evaluating or generating your predictions for every yi in your test set from, let's say, the regression coefficients that you learned in your training set. So you learn a model, take those regression coefficients, plug them in with a new set of x in your test set, and see how well you predict your new set of y's in that test set. And then you can compare it against the training error, which is different. Training error, you take the regression coefficients that you learned from the x in the training set, and you see how well you can predict y. Now, because, let's say you used ordinary least squares regression, x and y are actually used in the fit process itself. Remember, you learn those regression coefficients by minimizing the residual squared error on y trained. So you're always going to do better in your training error than your test error. Now, in the prediction context, really what you want to look at is solely in the test error range. The test error is your gold standard. And the null that you're trying to reject is that this regression coefficient, or this model that I learned in my training set, will predict y better than the mean of y itself. Why is the mean of y the null here? Because if you only have a distribution of observations and you don't know anything else about it, the best guess for its value is going to be the mean. Statistically, that's how that works. So if you have no other information, your best estimate of y is the mean. And the goal is to learn a model that does better than that mean. And you can only really evaluate it in the test error context, because your training models are often using y in the training set in order to learn your model. So it's automatically going to do better. So you need to be able to set out these test sets and training sets in order to conduct this type of validation on your null, in this case, the mean of y. Now we're going to go over two types of validation approaches, or cross-validation approaches, and they're actually two variants of the same thing. First, we'll go over leave one out cross-validation, and then we'll go over k-fold cross-validation. And keep in mind that these are just two variants of the same thing, and I'll explain at the end of the lecture how. The simplest way to think about how to build a validation set with a single data set is using leave one out's cross-validation. The logic is quite intuitive and simple. Let's say this is my full data set. I have n observations, p variables, and x. In order to do leave one out cross-validation, what you do is you iteratively go through your data set such that every observation has a chance to be the test set once. So in this case, let's just start with the first observation. Observation 1 becomes my test set. So I take it, and my goal is to learn an f-hat train, a model, from the training set, all the other observations, and then evaluate the test error on this observation here. So I'm going to take observation 1, so y1 and all the observations of x in the first row, set it aside, and then I'm going to learn my model. I'm going to fit a regression model, f-hat train, using all the other observations, so observations 2 through n. That becomes my training set. And so I just calculate the test error by plugging in all the observations in my first row, x1, into the regression model or whatever model I fit in my training set, and making a prediction for the first observation in y1. That becomes my error. In a regression context, this is the squared error on the residuals. In classification, it's just your classification accuracy. Now what we do is we just kind of repeat this and go through iteratively through the entire test set. So now I'm going to take out observation 2, hold it aside, and do the whole process again, whereas I take all the other observations that are not observation 2, make those a training set. So now I have observation 1, and then observations 3 through n. Those become my training set. I learn a model, f hat train, and then I apply that model now to the data from observation 2. See how well I can predict y2 from the observations in x2. And so that becomes, again, in the classification context, it's just the difference in accuracies. In the regression model, it's the residual squared error. You just keep doing this over and over again until you get down to your last observation. So now I have n observations, which means I do this n times. I take the last observation, set it aside as my test set. I learn a model from my training data, in this case y1 through yn minus 1 and x1 through xn minus 1. That model is learned, and then I again compare it to my holdout set, which is just that one row, n, the last row of my data set. I calculate it out. And so I just keep track of all the residual errors or the classification accuracies on all n iterations of the algorithm. That's it. It's pretty intuitive. Let me just kind of stepwise walk you through the algorithm here. Step 1, take all the variables from a single observation, we'll call that vector xi, and yi itself, and set it aside as a test set. Make a new training data set with all the not I observations. That little symbol there next to I indicates not I. So basically everything but that observation set aside. Now fit your model, f hat train, to that new data set that has everything but the holdout set observation. Then you evaluate your test error on yi from the model that you learned in step 3. You repeat these steps over and over, steps 1 through 4, for all n observations. So you have to run this algorithm n times if you have n observations. There's a lot of advantages to using this algorithm to evaluate your test error. First, you get a high-powered training set with which to estimate your model, and it also gives you a stable estimate of f hat train. So by doing leave one out cross-validation, essentially what you're doing is you're running n many replications of your model fit, where you don't include just a single test set, a single observation each time. So your test error is still completely independent of the model you fit. But where you had power, let's say with your original model, because you had n observations, with leave one out cross-validation, your training set only loses one extra observation. So it doesn't really take a hit on dimensionality in order to estimate out your training set. So you get stable, high-powered estimates of your training model. Also gives you this direct measure of generalizability. You are purely estimating test error because that observation isn't included in your model fit. It happens completely independently of your model fit. Now, leaving out cross-validation is computationally expensive. That's one of its major problems. You have to run this n times, and with sometimes, we're talking about this in the context of linear regression, which could often be an easy, fast fit. But if you're doing something more sophisticated, or it takes a long time to learn f hat train, let's say you're using a nonlinear model, you're using a deep nets, something that takes a long time to train, this can get computationally expensive really quickly. It can take a lot of time to run because you're running n many replications of your experiment and your model fits. It is also extremely sensitive to high leverage points. So if you have high leverage points in your data set, depending on where they sit in terms of being in a holdout test observation or the training set, you'll have this high degree of variability in your model predictions because essentially when every time you take out a high leverage point, you're changing the fundamental structure of f hat train. So it'll put a lot more variability in these predictions and impact your performance. There's also a strong negative bias in the context of regression when you use this in normal linear regression. What does that mean? Well, that means that you can often, if you have particularly an underpowered sample as it is, you're more likely to see null results in your prediction accuracy, or more likely to not do better than the mean, simply because it can be highly sensitive to these high leverage points or low power. So if you already have a low power data set or you have a data set with high leverage points, you can have a high degree of false negative results. Now, in order to kind of get around this degree of sensitivity to leverage points, computational expensiveness, and the negative bias, you could shift from doing leave one out cross-validation to k-fold cross-validation. K-fold cross-validation has the same logic. You're taking your data set and you're parsing it into test sets and training sets and iteratively going through such that every observation in your data set is in a test set at least once. But instead of doing test sets of size 1, you're going to do test sets of size greater than 1. The logic is that if you have n observations, you want to break your data set up into k folds. So for example, if I set k equals to 2, I have 2 folds in my routine. I'm going to break the data set up into 2 runs of a split validation. So in a 2-fold cross-validation, I'll take the first half of my data set it aside as the test set, and then the second half of my data set becomes my training set. I'll calculate out my errors from my model fits, and then I just do it again, but I flip it. So now what was the training set in my previous run, which we called a fold, now in the second fold becomes my test set, and vice versa. So in this context, every time I parse out the data into a test set, training set partition is a single fold. And you do your model fits, and you do your model evaluation. So you should have a vector set of model evaluations. In this case, I have 2 errors, 1 for each fold. The key here is that every observation needs to be in the training set once and once only. For a balanced cross-validation framework, you have to only let each observation be in the test sets once. That means each data point can be, or observation can be in the training set multiple times, and I'll go over how that works in a minute. But you can only have every observation be in the test set once. That's a critical criterion. Let's think about another example where we set k, number of folds, to 4. What this means is that I'm going to partition my data set into 4 equal size partitions. Approximately a quarter of the data set will be in each one of these partitions. So I can set one partition aside on my first run of the algorithm. I'm going to use that as my test error, which I'll show in blue here again. And I'm going to calculate out my test error based off of a model that was trained on the other 3/4 of the data, the other 3 partitions. I collapse those together, estimate f hat train, and then I use f hat train to build my model predictions of the observations in this last fold here. That will give me a residual squared error estimate, which we'll just call E1 here. And then on the next fold, fold number 2, I'll move up to the next segment, the next partition. So now what was the test error partition in fold 1 becomes part of the training partition for fold 2. And another one of the partitions is now used for my test evaluation. So just like before, I'm estimating out the residual squared error here, because this is just a linear regression context, based off of a model that was fit using the other 3 partitions. So it's still a holdout test evaluation. On fold 3, we do it again. We go back. What was the test partition in the last fold now becomes another training partition again. And we have the observations in this second partition or third partition here become the values that we use to do our test error evaluation based off the model that was trained using the other 3 partitions. On the last fold of the 4-fold cross-validation, we do the same thing. So we have now 3 errors that we summed for each one of the folds. What we just want to do now is collapse them all together into a single cross-validation error. So for every k in my k-fold cross-validation, I'm going to estimate out a sum squared error, and then I just sum those together, and that gives me my cross-validation accuracy. It's the average cross-validation error for all 4 folds, or all k folds of my algorithm. That defines your performance. What I'm showing here is the error for a regression model. It would just be an accuracy, classification accuracy for a classifier. So the logic works both for regression models and classifiers. I just chose to use regression for this context. So the algorithm is quite intuitive. Step 1, take unique subsample of m observations where m is just n over k. So if I have k equals 4 and n equals 100, then m is 25, which means that every partition has 25 observations. This is an approximate if you can't have an equal breakdown. If n divided by k does not come to a whole number, there's some approximations you have to make. So some of your folds might have 1 observation or 2 observations more than others, but they should be approximately equal. Now you're going to take that subsample of m observations and set it aside as a test set. You're going to make a new xtrain training data set with all not m observations. So for observations included in all the other partitions except for the one you're using in this fold for the test set. Learn or fit a new model to that training set. And then evaluate your test error on yi from that model that you learned in step 3. And repeat steps 1 through 4 for all k folds. And finally, evaluate the full set performance by summing across all of the evaluations that you did on each one of the folds. Now you notice this is very similar to the algorithm that I presented for the leave one out cross-validation, and that's because they're pretty much the same. Your folds define your variance of your model. So you need to balance essentially the bias variance trade-off here in your cross-validation. Just like before, you can have models with very low bias and very high variance. And what we're talking about now is bias variance in the context of your holdout set evaluations. So k-fold can span a range depending on k. The most flexible models you have are the case of leave one out cross-validation, which is a k-fold classifier where k equals n. So leave one out cross-validation is really just a special case of k-fold cross-validation where k is set to n. This is the most flexible variable version of your models. The most conservative generalizable version of your models are those that you evaluate using split half tests. And this is just the case where k equals 2. You just split your data into 2 partitions. this has more bias and less variance. It makes sense because as you increase K, remember, the size of your training data set goes up. So if I have the same number of observations, N, in a split half test, my model, f hat train, has half the observations of my original data set. Whereas if I use leave one out cross validation, where K equals N, my training data set that I use to fit a model on each fold has N minus 1 observations in it. So it's automatically going to have more power than the split half version of the same data set. That's why there's a variance bias trade-off in the context of cross-validation. And the goal is to try to find a conservative enough K that balances your costs of flexibility in your model and computational costs with the need for generalizability and a reasonable amount of computational speed. So there are some things to consider when you're doing cross-validation. First, you want to choose the K to have enough power in the training set to fit a reliable model. This goes back to the slide I just showed before. If you use a split half test or a two-fold cross-validation on a relatively small data set, you're going to have a very unreliable estimate of your training model on each fold. So you want to choose K effectively so that every time you estimate your training model, it's reliable. You want to have enough folds to reduce the model variance. So you also want to have enough folds so that you have a good degree of generalizability in your data. So this is why oftentimes people will skip out doing leave one out cross-validation and go for a 5 or 10-fold cross-validation. You want to balance your subsampling to watch for high leverage points. So you can watch for high leverage points. There's other reasons you would want to balance your subsampling when you set your data into partitions. So if I use a 5-fold cross-validation or a 4-fold cross-validation, let's say there's a factor that I know that's very relevant to my model, let's say gender. You actually want to use a scheme that doesn't arbitrarily choose observations. It balances the number of male and female observations that you have in your data set so that every fold has the same balance as your entire data set. That was just an example, but there's lots of cases where you want to have some sort of balance in how you partition your data set when you know there are factors that are relevant to your model prediction. And you also want to watch the dimensionality in the training set. If you have already a low-powered data set for the problem you're trying to fit, having a low k-fold validation, let's say a 3 or 4-fold cross-validation, might give you just too underpowered or too high dimensional of a problem. It's too variable, so you're going to have low performance in your holdout test set. So this links back to the first point on this slide. You want to keep a good mind or have some principled reason for specifying the dimensionality of the training set you use in every fold. And that will kind of help to balance this out. So you want to balance, you want to have dimensionality concerns and power concerns ahead in your mind when you determine what K is. But otherwise, you can see that this is a beautiful way for testing generalizability in the data set that you have. So cross-validation allows for you to directly test the generalizability of your effects without having to collect additional data. You don't have to go run a replication experiment. If you've got a suitable enough data set, and many of us are working with these days, you use cross-validation to answer the question that you want, which is how generalizable are the effects that I learn in the data set that you have.